AI can never be perfect, and there's actually a deep reason why. Let's start with what generalization is, as it's at the core of the argument. Think about the ocean and the bucket analogy I described in the first video. We want to understand the ocean ultimately. We want to deeply understand its patterns and all the things that are in it. But all we have is a bucket. That's all we have access to, a sample, a proxy. So what we want is to grab that bucket and see what information we can get about the ocean from that bucket. And this is fundamentally a generalization problem, from dataset to distribution. That's the conversion. We want to sort of find as many patterns as we can and learn from that data set. And ultimately, we want to see if that is applicable when we come to the real world scenario, the nature, the distribution, the true distribution. So it's like a partially observable approximation game, sort of. But what really is magical is that gap, the gap between the empirical risk and the true risk, the difference. And just as a recap, the empirical risk is the measure of wrongness or the error evaluated on the data set sample. So what we have. And the empirical risk is always computable. We can always do it because that's what we know. That's from the finitely large data set sample we have. The true risk is a hypothetical and it's an entirely theoretical measure of wrongness when we have access to the entire true distribution. And that's what we want to get because that's obviously the desired thing. The generalization gap is quantifies the quality of generalization we do. And generally speaking, a smaller gap means better generalization, while a larger gap means worse generalization. The supremum of the gap is the worst case generalization. Let's talk about the first source of error, bias. Bias is systematic error, and it usually indicates that the AI is too weak. This is called underfitting. Why does it mean the AI is too weak? Well, if you think about it, imagine you have a junior research scientist and he's trying to understand a really, really complex data set sample or bucket in our analogy. If the scientists cannot understand it properly because they haven't encountered this before, then they'll make systematic mistakes. It cannot expressively learn patterns from the dataset, so it makes systematic mistakes. This is called underfitting, and it happens when the AI is too simple and thus cannot fit to patterns properly. When we observe this, we can usually see it as the high train error or high empirical risk. So it's bad on the training data set and high test error. So it fails to generalize too. It's also bad on the true distribution. It's also bad when we apply that to the real world. That's called bias. The second source of error is variance. And it's sort of the opposite in the sense that it's not really systematic, but more like fluctuating. It means that the model is highly sensitive and unpredictable. And it usually indicates that the model is way too complex. Why does it mean it's too complex? Intuitively, we can think of this as a fickle or indecisive person who keeps overthinking a decision way too much and keeps switching around one time like this and then another time like that. And thus, because they're overthinking it so much, making this so complex to figure out, they bounce around and become very sensitive and thus also fail to generalize. There is not enough data or diversity. That's also another cause of high variance. And the result is that the model memorizes the data. It thinks that the data that we train on, the sampled data set, is the ground truth. not even considering the DGP, what we really want, and thus it fails to generalize too. This phenomenon is called overfitting, and it happens when the AI is too complex. What we observe is it fits the sample dataset really, really well with low train error. So it's really, really good on the actual dataset because its complexity clearly works. But it fails to generalize to the true distribution. The second we test it on the real world data, on the everything, it yields high test error, meaning it's really bad at the other thing because it treated the sample data set as the ground truth, as the actual thing. And this is called variance. The third one is a bit different, and it's called irreducible error. It's error that is intrinsic to the distribution itself. This could be noise, natural variation, or randomness. Because it's intrinsic to nature itself, it's the inherent variability and the randomness in that distribution. It cannot be reduced. It's inevitable. It's the only kind of error that we cannot sort of reduce. So we can't get perfect on that. If the irreducible error is 0.5, for instance, the model can't go below that error. That's like a lower bound. It's the minimum we can do because we cannot reduce that at all. We can't minimize it. That's like the limit, basically. If it's 0.2, that's the best possible model cannot go below 0.2. Yeah, so it's basically it cannot be reduced, no matter what. So what's the trade-off behind this? If we make the model complex, then it yields high variance and low bias, or overfitting. It memorizes the dataset and fails to generalize. If we make the model too simple, it's too weak. It yields high bias. It can't fit to the dataset and learn. It can't even fit to the own dataset sample, but it has low variance. What can we see here? It's like a balancing act. We want to sort of balance out variance and bias such that we can make the model just right to minimize both variance and bias. So that's like the overall error. We want to account for both, not just variance, not just bias, but both. What we can see here is that every single AI, or more generally, everything and everyone, is a bias predictor. Not one or two, everything and everyone is and always will be a bias predictor. Because it's like a partially observable problem, right? We optimize parameters for the sample dataset, which in this case, the dataset is what we can see, what we know, and our perspective on it, our local restricted view. But it's not the true distribution. It's not the global ground truth. And that's what we want, but don't have access to. If you think about it from the analogy of eyes, for instance. If you're in a park or zoo and you're trying to look around, your eyes can't sort of capture everything at once. You only can see a set like perspective at once. Like you can only see right in front of you, not behind you, obviously. If you turn, it moves. But at a time, you can only see like partially of it. So you can only see a local view of it. And that doesn't reflect the global truth, which is what we really want. So the objective is empirical risk minimization, not true risk minimization. So every single AI is always going to be biased, subject to the incompleteness, the variance, the noise, and the quirks of the empirical data set. It's what we can see, and we make assumptions from that, even when it's not always applicable to the true distribution. To recap, bias is systematic error. And variance is fluctuating error about how sensitive or unpredictable the model is, and thus it memorizes the dataset and fails to generalize. Irreducible error is inherent variability in the data. So that's the only one we cannot reduce. It's the one that's inherent to the nature itself. Underfitting means the model is too simple, and overfitting means the model is too complex. Thank you.